Good morning, everybody. Welcome to the Friday Fellows meeting. It's my pleasure to introduce Dr. Dustin Long. So Dr. Long is an assistant professor in the Department of Biostatistics. He joined UAB about a year ago, coming here from West Virginia University. So I'm sort of partial to West Virginia University since that's where I'm from, but I'm also happy to have Dustin here at UAB. So he's going to be talking to us about continuous data. Thank you.
Thank you. Good morning, everybody. It's 8 o'clock in the morning. The energy flows both ways. So let's try this again. Good morning.
Good morning.
Okay, thank you. Well, I'm like Dr. Levtan said, my name is Dustin Long. I am a professor of biostatistics. And today I'm going to talk about summarizing and analyzing continuous data. One sample, two sample tests, and ANOVA. So a little background about this talk. As Dr. Levtan mentioned, I came here from West Virginia University. And while there, I was part of our clinical research, design, epidemiology, and biostatistics core of our CTSI, which is equivalent to the BIRD core for your CTSA here. And we decided that throughout all of our partner sites and our trainees at West Virginia at the university, we wanted to give them a stats crash course. So we planned a day and a half course in which we went through all the major topics of statistics. Continuous data, categorical data, linear regression, some higher functioning things like machine learning, an introduction on how to use the statistical package called R. It was a kind of a fun day and a half, as much as fun as statistics can be. I know some of you are laughing and smiling because not your favorite course in your program probably, but that's because you haven't had me. Now, so this talk that I'm giving is the first half of the two continuous data talks that we gave at that short course. So I go up to ANOVA, so group comparisons. The next presenter talked about linear regression and how to do different kinds of regression. So that's not part of this, but if this is something that you're all interested in and you all get something out of this talk, then maybe sometime later down the road we can work that talk up and I can give that to you as a kind of a continuation of what we talk about today. So again, thank you all for inviting me here, and it's a pleasure to be here. The way I do my talks that are this kind of talk, meaning this is not a big forum, this is more of an intimate setting, is I like questions. I have a slide at the end that says questions, question mark. But I prefer questions in the middle. I prefer a discourse because I feel it makes me give better lectures and it gives you all better understanding. And some of the topics we're going to cover are very simple, but hopefully I'm presenting them in a way that's a little bit different and maybe a little bit more clear than what you've seen in the past. So, There we go. I can run a computer. So the outline of my talk today is an overview of what is continuous data, and then we'll talk about the main issues that you deal with and main topics with continuous data, measures of central tendency and variability. Then we're going to talk about graphical representations of data. Then we're going to talk about 1 and 2 sample tests, and then we'll talk about ANOVA. So continuous data. Whenever you take a statistics course, intro probability and stats class, anything like that, we talk about defining data as continuous or discrete or categorical. Those words are interchangeable. And what it means is, how do you measure them? Well, continuous oftentimes get broken down into interval or ratio. And in fact, I've actually had reviews and articles that I've written come back and say, well, is this an interval measure or a ratio measure? Well, what an interval data is ordinal data with meaningful distance between values. So if you have some string of data and a distance between, say, a 0 and a 1 is meaningful, then it's considered to be interval. So think about it in terms of birth weight. That's my go-to answer when I talk about clinical continuous data, is birth weight. Because magically, birth weight is one of the few truly normally distributed data in the world that come from a human. Most of the stuff you can fudge normality, which we'll talk about later, but birth weight is typically pretty good. So a birth weight of 1 kilogram and a birth weight of 2 kilograms, that's a meaningful distance. 1 kilogram increase means something, so it's interval. A ratio data is interval data that has a natural point at 0. So that means something that says a 0 has a meaningful value comparatively to something else. So what's an example of something that has a value of 0 that might be interesting that you measure on a person? Not a lot of values with 0 for a human, right? I mean, unless you want to go to temperature and you say this person's 0 degrees Celsius, probably still not a person, right? Probably an ice cube at that point. The reason I introduce these and talk about them is because nobody cares. You're going to see these in all the books, and if you take these courses, you're going to have questions about interval versus ratio variables, and you're going to have to, is this an interval ratio? It doesn't matter. We only really need to differentiate in terms of our discussion today, and when you're going to do analysis, between is it continuous, meaning I can get any measure possible, like birth weight. We normally round it up because our scale can only go so much, or because we think about it only in integers, but it truly is continuous. I just had half a bagel. My weight just changed incrementally, probably more incrementally than I would want to admit. But that kind of data, continuous data versus categorical data, which is data that are only in bins. So like race. Race has a finite set of bins that you can fall into, and you can't technically fall into more than one bin. Race is probably not the best example. Most people try to use sex as the example. And sex is binned, but you can't use gender, because gender is a more sparse measure. So a better example would be BMI category. You're either normal weight, overweight, obese, underweight. Yeah, there's 4 of them, right? So you're in one of those bins and one of those bins alone. That would be considered a categorical measure. Or it's a yes-no. You have a disease, you don't have a disease. Those are considered discrete measures. So we want to just differentiate between continuous and discrete. I learned a phrase early in my career that was called sleeping with your data. And I have stressed it in every class that I've taught, to the point where the first class I taught at North Carolina as part of my doctoral program, there were students who were part of the maternal and child health group. They made me a shirt that's over in my office that says he sleeps with his data, because I said it so often. And that's really the key to starting out any kind of analysis, especially with continuous data, is to sleep with it. Look at your data, study your data, get an idea of your data, not just in terms of the numbers themselves, but in terms of how they were collected, what study design were used. All of that plays into it. Here we have an example of data, and this came from a statistician from my master's program. This is just a small set of data that represents a larger data set. The statistician was working with this data and was trying to do some analysis. And something just fell off. They just fell off with the data, and they looked at it and studied it and couldn't figure it out. Well, finally, they looked at this data and realized that there was a pattern in it. There are only 9 points here, but does anybody see a pattern with this data? Well, it's hard to see, but because there's only 9 of them, but no data point had above a 0.4. There were only 0, 0.1, 0.2, 0.2, 0.3, 0.4. There were no 0.5s, no 0.6s, nothing above 0.4. And the statistician, when they finally realized that was the case, they're like, oh, okay, something happened. How do I find out why this data are like this? Because it didn't stop at a certain value. It didn't stop at like 2, because there's still values above 2, but there was never a value between 2.4 and 3. So he went to the person who was collecting the data, and they happened to be collecting data on, I can't remember exactly what they were weighing, but they were weighing things on a scale. And it was a scale like those that you see in the grocery store, where there's an array of numbers kind of on a semicircle, and you put it down and the arrow goes and it points at a certain value. Well, it turns out that the person, I normally have a board with this, but there was this weight of 1, and then there were 4 little tick marks, and then there was a weight of 2. And so they counted the tick marks as 0.1, 0.2, 0.3, 0.4, 2, as opposed to which it should have been 0.2, 0.4, 0.6, 0.8, or kind of if it was in the middle, you would try to have guessed it. So what happened was the person that was collecting the data used the instrument incorrectly. And so the statistician was able to see through the data examining, sleeping with their data, that something was wrong, but they went back to the data collection and was able to figure out what the issue was so that they could fix the data. Now, one time when I told this example, they said, well, is it really going to make that much of a difference? Is it really going to, that 4.2 is going to become 4.4? And, in this example, when you're weighing something like that, it might not make that big of a difference. But what if these were doses for a chemotherapy that had been written down incorrectly? It might not have made a very, this is a silly example, weights and scales and things, but knowing what's going on when there are simple examples really helps you realize that we need these techniques everywhere. Because, yeah, the means were probably fairly close, and if you're comparing 2 groups, overall it should be average out because of the large law of large numbers, or some, mathematical mess that we talked to you all about in class. But the key is it would have been wrong, and you could have fixed it. And that's where these kind of diagnostics or sleeping with the data can come in. Because anytime you can make your model better or your data better, you should do it. Especially when it's something as easy as going and finding out how the data were collected. No estimation or inference should be performed on data that has not been verified. So you want to make sure that everything is correct. Some examples of this would be, I've gotten data from large electronic medical records before, and you sometimes get data that are weights or heights that are a mixture of centimeters and inches or pounds and kilograms. And sometimes those are easy to pick out. Sometimes it's really easy to find, oh, this is a weight in kilograms, not a weight in pounds. But somebody like me who's a little on the heavy side, my weight in kilograms would look like a smaller person's weight in pounds. So if you don't know what my measurement should be, then you could incorrectly assume my weight to be in pounds. So you need to make sure that you're clear. My favorite example of data coming to me in a mess in electronic medical records, and I'm sure, Emily, you have examples too, is in temperatures. Every third or fourth temperature was in Celsius versus Fahrenheit, which luckily it was all in humans, And so it was really easy to tell which people were in Celsius and which was in Fahrenheit, because a 32-degree Fahrenheit human is dead, frozen. But a 32-degree Celsius human is almost right. Was it 32.7? 37.2? There we go. I had the numbers. They were there. Close. So the best practice is to summarize the data into meaningful statistics that can be evaluated. So looking at a ton of data in an Excel sheet or in something else like this person ended up doing, is not normally the way you would start. Normally you start with looking at data in meaningful statistics. Well, what are some meaningful statistics? Well, the first thing you want to do is look at what we call central tendency, which is a big fancy word for the middle of your data. Because typically, even if we're dealing with data that might end up being not centered or skewed data, we want to know where the middle is. But there's several definitions of what middle can be. So who can tell me what the mean is? What is the mean of a data set?
For any given variable, it's the average.
How do you take an average?
You sum up all the data points and divide them by the number of points.
Okay. That would be considered the arithmetic mean. There's also a thing called the geometric mean, where you take all the data points, you multiply them together instead of adding them, and then you take the nth root of them. That is also a measure of central tendency that's called a mean. There's also a thing called a Windsorized mean. Windsorized means you've probably seen them and not realized them. Anybody ever watch the Olympics and like figure skating or any other or gymnastics, and where they'll get this string of judges' scores and they'll throw out the high score and the lowest score and then they'll average those that were left? That's called a Windsorized mean, where you get rid of a certain number of outliers on both ends and then you only average the middle. So when you say mean, you also have to be clear about what you mean by it. Typically, we won't play tricks on you like that and say, I want the mean, and actually mean the geometric mean. We'll specify it, but understand that just summing up the data and dividing by n is not necessarily the only mean available. How about median? Anybody know what the median is?
Middle.
What do you mean middle?
Well, you'll be lucky with odd numbers, so that would be the exact middle, like between the. Well, it's something that would cut the data in half.
That's the word I wanted to hear. Half. Half the data is above it, half the data are below it.
Yeah.
Because it's not necessarily the middle of the picture, because it's actually the point. If you imagine, if you take your data as a pile of sand, and you take your pile of sand and you shape it to whatever the data look like, where it's skewed over here, or centered, and you have this data on a yardstick, and you want to put your finger on this yardstick such that you can pick it up and it won't fall. That value where you put your finger on this pile of sand that is your data, that is the median, because it perfectly balances this data. So that's the middle. And if your data are skewed, the mean and the median won't be the same. The last one is mode, and that one's probably the least used, at least with data for humans in clinical trials and those things, because mode is the data value that was observed the most common. For continuous data, you typically think about it in terms of a range of data, like between ages between 24 and 36 are the modal band. But the actual mode, the number that observed most, we don't really do that. Also, we have variability. How variable are the data? How spread out are my data? And the typical measures there are the range, interquartile range, variation, and standard deviation, which we'll go into those more in depth. So we've already talked about these a little bit, but the mean is the sample average of the data, and it's the arithmetic mean. And what I have here is that it's sensitive to outliers. Now, what is an outlier? I just threw that word up here without definition.
I mean, if you like have a set of data points and they're all kind of you know, focused around a certain range of values, and then you may have something that's like way out there, you know, complete like a lot higher, a lot lower than what you're seeing for most of the data, then that would be considered an outlier.
That's
kind of, yeah,
Yep.
a less elegant way.
that's not, you know, and that's the thing about outlier is determining on what you're doing, the definition of outlier changes. Had we been doing linear regression, there is a formal specific definition for an outlier in a regression model. When dealing with just data and looking at data and talking about outliers, there's not really one that's better than any other. But the thing I would want to say about outliers, and especially when we're talking about mean and median, is that you need to understand also that it's a function of the true range of the data. Because you could get a value that, like, what's your name? Matt. Like Matt said, where most everybody's here, but then you have somebody way down here. That's some value. It could be that that's still within the plausible biological range of your data, so that there's actually nothing wrong with that value. It just happens to be very different from your other population. What I teach in my classes is that then we need to look and make sure that this data are verified and it's true, and then it's going to be a real hard decision about what to do statistically. Because I would say if it's biologically plausible and you verified it, that you can't just throw it away. And most outlier techniques say, oh, just get rid of it. So you don't want to get rid of it, especially when you're dealing with clinical trials or when you've paid thousands and thousands of dollars for people to be in a study, and then you go, oh, well, this person's outlier, let's get rid of them. You might be throwing away tens of thousands of dollars of work, of data. So you want to be more cognizant of it. But the mean is very sensitive to outliers. And this is my favorite example of mean. I went to the University of North Carolina. I don't know if you all are familiar with their basketball program, but it is somewhat famous. And the most famous basketball player ever, potentially, is a man by the name of Michael Jordan. If any of you are huge buffs, do you know what his undergrad major was in? Geography, right? Because athletes sometimes, especially in North Carolina recently, have not had more rigorous undergraduate degrees. When the University of North Carolina would report their average salaries for different majors, they would include Michael Jordan's salary in that average for geography majors, so that we would look down here, oh, if you majored in math, it's $60,000. If you majored in English, it's $45,000. You majored in geography, it's $375,000. What? I'm going to major in geography. So it was very sensitive. His one observation pulled all the average way up there. So the more likely statistic we want to use there would be the median, the value that has 50% on either side, because his value way down here may have moved the median a little, but it would only moved it one observation. It wouldn't have moved it way out of the range of the data. So median is much less sensitive to these, or what we use the word robust, to these kind of extreme observations. The median is also the value, if any of you are going to do cost effectiveness analysis or cost analysis with money, median is the value you really want to deal with money most of the time. Example would be if you're looking at houses on a street, you wouldn't want to use the average cost of the houses. You'd want to use the median of those houses, because one very high house, one big monster mansion like you go to Mountain Brook, is going to throw off a street. Or on the other hand, if you have a more affordable house on a street with lots of mini mansions, that will drive their price down. So median is a much better one when you're dealing with money issues. And again, for those of you who just came in, I like discussion. So if you have questions or comments on what I'm saying, please feel free to step in and discuss, because I don't like hearing myself talk for an hour. It gets boring for everybody. The mode, again, is the most frequent value observed in the data, but it's kind of useless when you have truly continuous data. I like to mention it and then say you probably learned it, but I'm not going to use it much.
I do have a quick question.
Yes.
So it's easy for me to understand when to clearly use a median versus a mean, but sometimes I wonder when, if ever, the mean is clearly better than the median.
The word better is the problem in your sentence.
Okay.
There's times in which the mean is more appropriate.
Of your data? I don't know. Or more appropriate. Okay, let's go with that.
And a lot of, so that's a good question. That's a good question because when I worked with investigators and we're doing table 1s, right, the demographic table, they want to know, do we do means and standard deviations, or we do medians and interquartile ranges? And I would say, well, what statistic are we going to then run? If they ran a t-test or an ANOVA or something that assumes normality, those tests are for the mean. So it makes sense for us to present the mean. However, and I don't have this in this talk today, if you were to doing a non-parametric test, such as a Wilcoxon rank sum test, or if you use a Mann-Whitney test, as some people call it, or those things, then those tests are kind of on the median. And so I would want to represent medians then. So technically it's what goes downstream. What I like to do when I create those tables, I do both. I'll have mean and standard deviation and median and IQR. Because it gives, the two together gives me the fuller picture. Because, like I said before, I like to sleep with my data, and those pieces together give me a better picture. Almost always when you go to a journal, they'll want one, and I have been dictated to journals which one they want. Even if I did a non-parametric test and wanted medians, they will request mean and standard deviation. So there's not an answer to your question. Which is one of the things that's the point later in this talk, is that a lot of what we do is an art form, and it really flows from what's needed at the time. So I would make it a point to start thinking about both of them and presenting them both, and understanding that when you're doing parametric things, t-tests and whatnot, and regression, the mean is more appropriate, and then if you're doing non-parametrics, it's the median. Did that help or confuse?
No, it does. I've never thought about even thinking that step ahead about which tests to use. I think that's helpful. Thanks.
Yeah, no, that's good. Good question. Please, that's what I like. We like the questions. So those are the measures of central tendency. Where's the middle of my data? These are the measures of variability, or some of the measures of variability. The range is literally the maximum minus the minimum. So how wide are your data? Which typically is just given in units. So if the distance happens to be 100 to 150, then it's just given as a 50. So it's not that useful of a value when you're trying to do analysis or thinking, but it's good to look at your data and think about it, especially when you're trying to figure out outliers. Because if you've got this enormously spread out data, and one example of some data I'm looking at now is we have vitamin D measures. Calcitriol, I think I said that right. Calcitriol measures, and we have everybody here, but we have somebody above 200, 220, and everybody, all of my co-investigators are like, oh, that's a really big range of the data, because normally you don't see people with that value. But then you kind of go on. That would be not what you report. Typically what you report is what's called variance, which is defined as the average square deviation from the sample mean. And then here's a formula, because you can't have a math talk without some kind of complicated formula up here. But basically what it says is that we have this arithmetic mean in the middle, and every observation is somewhere relative to that mean. I take the difference between each observed point and that middle point, the mean, and then I square it, because if I didn't square it and I tried to sum them up across them, it would just sum to 0. And so I would say, ooh, variance is 0. So I square it. You may say, well, there are other things you can do to make values positive. I could do absolute value. I could do to the 4th power. I could do other things that would allow it to be positive numbers so I can sum them. But it turns out mathematically that if you use the square, you get a lot of nice properties. I don't really know if the properties were found before, or if they went back and retroactively made it squared. But if you do this, where you take these little deviations from the mean and you square them and sum them up, it becomes what's called the sample average when you divide it by n minus 1. For the mean of the data, we summed up all the data and then divided by n, the number we had. But here we divide by n minus 1. Does anybody know why we do that? Why is it not divided by n? Because I sum up n things, sum up, say, 100 things, but I divide by 99.
Because you're taking the difference between each one, so you start one behind,
You have to start one behind?
but
Take out the
2 minus 1, 3 minus 2. So you're not going to do 1 minus 0. So that's what
I think you're getting at the same concept that I'm about to say, but I'm not quite sure, but I think we're on the same page. If you do all these little subtractions, the last one, so if you've gone through all your data, the last one isn't free to move around. Because if I fixed my mean to be, say, 5, and I do all these subtractions, that last one has to be the value that makes x bar be equal to 1, or that value summed to 0. So what we say is, because you've estimated the mean, we have x bar, it's an estimate of the mean, I lose what we call a degree of freedom. Because that last one is not free to be whatever value it wanted. All the other values were. It could have been 10 away from the mean, or 2 away from the mean, or exactly equal to the mean. But that last one has to be a fixed value to make sure the mean stays the right value. So we lose a degree of freedom. That's why it's n minus 1. And there's also some mathematical stuff about unbiasedness and things that we're not going to go into that why n minus 1 works. But that's the sample variance. And then if you take the square root of the sample variance, you get what's called the sample standard deviation. Typically when you report, and this goes back to your question, when you report your variability in your data for journals and those things, you don't report the variance, even though the variance is what you calculate. You report standard deviation. Does anybody have a guess at why we report standard deviation rather than variance?
Kind of helps you describe your data in terms of like discontinuous, in terms of like distribution. So talk about the distribution of your data.
I think you're getting there. So what you're trying to say is that there's a rules with the normal distribution that says if you're 1 standard deviation away in positive or negative, there's 65% of your data are in here, and so on and so forth. What would the units be for the variance? The mean is just the data summed up and divided by n. So if we're thinking about it in terms of weight, we use pounds because I'm trying to teach my son pounds and he doesn't get it, so we're talking about it a lot at home. Pounds. The mean is also in pounds. If everybody's data are in pounds, the mean is in pounds. The variance is a difference of pounds squared. So the variance units are pounds squared. The standard deviations units are back in pounds again. So by reporting the standard deviation instead of the variance, I'm now reporting it back on the units of the original variable. So that I can do what I think you were trying to say is that, it's the average is 10 plus or minus 2 pounds. If you use the plus or minus 2 notation. Plus or minus notation. But it's the units that really kind of why we like standard deviation more, at least in my opinion. So these are the measures of variability. So now we've looked at numbers. And numbers are great, numbers are good, but numbers are not as pretty as graphs. You know, what's the old phrase, picture's worth 1,000 words? I can tell you idioms all day long, all right? But I want to show you what that means. The 2 basic graphs that we're going to kind of talk about briefly here are histograms and box plots. And you all probably done those in classes at this point, right? Oh, I should ask, who all has taken a biostats or stats class before? How many of them have taken them here? Several of them here? Was it in biostats or was it in another department? Stats. In biostats. Okay. So a lot of this is familiar, but histograms and box plots. The box plot also has another name. It's called a box and whiskers plot. You might have heard it called that. And I'll tell you why it's called that in a minute. And then there are scatter plots, which we're not going to talk about scatter plots. That's reserved for the regression discussion. But those are the 3 kind of main plots that you do with continuous data, at least initially. A histogram, the data are binned into ordered categories, and percentages or frequency is plotted on the y-axis. So here is some made-up data in which we plotted some data and each bin, and I put the value of the bin on the top. So this is the bin that represents 34, but could you tell me, is that 34.0 to 34.99, or is it 33.5 to 34.5? So what does that bin represent? Histograms are great. Histograms are a useful tool, but if you don't label them correctly, they're kind of useless to the audience that you're trying to present them to, because I just put a 34 up here, or a 40. Right? That could be the midpoint of that bin. That could be the range of that bin. It could be whatever. So histograms are great. You want to use them, but you need to be careful about making sure they're labeled correctly so that the reader can understand. You may get it. I wrote the code. Of course I know what it is, but the audience might not know. The other issue to point out is that this is frequency, meaning the height of these bars is literally the number of people in each bar. So one increment there represents one person or one observation in my data set, such that that 37 represents the most number of people in terms of frequency. Frequency is one way to do a histogram, but technically some books don't call this a histogram. They call this a frequency plot, not a histogram. A histogram, by some definitions, is only by the percentage, meaning this height of this bar, this first bar, this 34 bar, would be that number of people divided by the total sample, such that each bar would add up to, the sum of all the bars would add up to 1, or to 100% if you did it that way. And why percentage is preferred? This is two histograms of two different samples of data. The dark red sample has many, many more people in it than the orange sample. So if I'm trying to compare my histograms, my data distribution between the red and the orange samples, this doesn't really help me that much because it's total number of people. Now, clearly this example that I've drawn, you can see that the distributions are different. But because it's total number of people, it's not as easy to pick out. Had it been percentages, I can put two differently sized distributions side by side and see two different pictures. Say I'm looking at males versus females of some kind of outcome. And I can see their distributions, even if I only had a third of the amount of males as I did females. And I can compare if that distribution is the same. If I used frequency, or in this case, number of people, that would be much more difficult to do a comparison. So my recommendation to you is if you're looking at your data and you're wanting to run a histogram, make sure it's doing percentages or density is sometimes the word you'll see. Questions, comments?
Would that not be a Pareto chart? Like if you use percentages, I mean, if you didn't know how to write, but Pareto charts, and it adds up to 100%, all the different ones.
There are a couple of things that I know of that are called Pareto charts, and I'm not exactly sure. I'd have to see which one you're talking about. But if you're talking about R?
No, we use it in quality improvement measurement, so to see which.
That's the one that looks like this, right?
Yeah, you put your highest one first, and then it like goes down and descends the order of them, so you can see where you should prioritize.
Right, and that one. That would be different than the histograms we're running here because our x-axis is a continuous measure. So I can't reorder my bins based off of something. Whereas that one is more flexible and you would stack it based off some priority system. And it also, is that not the one that looks like a violin? No, that one's not the one that looks like a violin. Do you know what I'm talking about, Emily? There's a histogram or there's a plot that I think it's sometimes called a Pareto plot that looks like a violin. So it looks like a histogram coming off this side and a histogram coming off that side.
Oh.
And I've never run one.
I've seen those. I don't know.
I've seen them for like population distribution kind of.
Yeah.
Yeah, I don't remember what they're called other than population
I can't
distribution charts, but
yeah.
I've seen those.
But that would be the main difference between what you described and this would be this has got a fixed x-axis, fixed continuous variable there. And this is different than a bar chart. You also may have seen bar charts which talk about percentages in each category of a categorical variable. So like a dumb example would be I've got 40% blue cars and 10% red cars and 30%. That is not a histogram. That's a bar chart because those categories on the bottom are fixed categorical measures, not a continuous measure. They look the same, but we would call them different things. Good. Box plots. So this visualizes what's called the 5-number summary. The 5-number summary is the, to me, it's like the appetizer to your analysis. The 5-number summary is the minimum value, the 25th percentile, meaning the value in which a quarter of the data are before it, the median, so the value where 50% of the data are before it, the 75th percentile, and the maximum. So these 5 numbers completely describe the distribution in terms of how spread out it is in the middle and what the ends look like. And that's what this box plot gives you. Now you might notice that for this particular box plot, there are dots below this bottom, what we call a whisker. And that's because certain softwares do things differently. That's on the next slide. But I'll come back to that in a second. But basically, this bold bar in the middle is the median. And then there's a box that's drawn at the 25th percentile and the 75th percentile. So in theory, then the 50 middle percent of my data, the middle 50%, is in that box. And that's where it gets its name, box plot. And then you have these things going off the ends, which are sometimes called whiskers. And where the whiskers end is, I don't want to say arbitrary and relative, but it's pretty arbitrary and relative based off of your software. So here, this one goes up, and then there's still an observation above it, and then there are 4 below it. And then on the second one, which is a non-symmetric data, so this was generated from what's called a gamma distribution, you can see that it's much more squished down at the bottom, and then we have a bunch of outliers there based off of its definition of outlier. Which software you use, the whiskers can include the maximum. So if you were to run this in SAS by default, SAS would make it to where these values, this value at the top here and the value at the top over there would be the end of the whiskers. So you would have no dots floating around outside of the whiskers. So it literally uses just those 5 numbers. But other softwares such as R, if you've used R, that's what this was created in. It uses 1.5 times what's called the interquartile range, where the interquartile range is the difference between the interquartile range. You have to be clear about what you mean, because you'll see it defined both as the difference between the 75th and the 25th percentile, so literally the distance between them. But you'll also see it defined as those 2 numbers together. So you have to be careful what you're talking about when you say IQR, interquartile range. Is it the difference, so it's just a number, or is it literally the 2 numbers? Well, for a box and whiskers plot, it uses that difference, that distance, and it multiplies it by 1.5. And then goes up 1.5 and down 1.5 by default, which is one of the reasons why you get something that looks like this. Now you may be asking, well, why doesn't it go down further? Well, it stopped it at 0 because I told it to. Otherwise, it would have wanted to go down further on the bottom because it wanted to go 1.5 the IQR that way as well. And then what R does is it says, well, anybody outside of that range gets dots. Because if you're more than 1.5 interquartile ranges away from the other quartiles, that means you're an outlier. And SAS can do both. SAS can make it to where there are no dots or there are dots of certain length. And you can also specify different values of what the whiskers do. So that goes back to Matt's point about outliers. What is an outlier? Well, the definition of outlier in this box plot would be any value that's more than 1.5 times whatever that range happened to be. Box plots are really useful, especially when we'll come back to these again when we talk about multiple group comparisons like ANOVA. Are there questions about the box plot?
Why would you do the non-symmetric versus symmetric?
I just wanted to show you what they look like. So the first data were generated from a normal distribution, a symmetric data. And so that's what a symmetric data looks like. You see how it's kind of, the bold line is in the middle of the box, and the whiskers are about the same length, and there's very few outliers. This would be what a symmetric data would look like. The other is generated from a gamma distribution, which is a very skewed distribution. So then you can see, I don't know, can I move around? Am I allowed to move around? Okay. I just don't want to mess up the camera, right? I don't know. Maybe I can do it with the mouse. Hey, here we go.
I guess my question was, why would you do the 1.5 times IQR? Like, why would you do that? Is that better for a non-symmetric data set or something, or?
It's if you want to try to get the box plot to tell you what values are extreme. So for this non-symmetric data here, you see there's a ton of points that are above here. So this would scream to me that this is very, very skewed. And not only is it very skewed, there are a lot of points that are outside of this range that would tell me if it was nice and balanced data, i.e. symmetric data. So this is really screaming, not only does this part down here, the whisker down to the box and the box itself tell me this is skewed data, but the fact that I have so many, quote, outliers really says that this is non-symmetric. If I had just put the whisker up to this point here, and I had a straight line here, it wouldn't have given me an idea of how many points lied there. It would only have told me that the most extreme was at that very high value. Same thing as this one. They would have been about they're not the same scale, but they would have been about the same place here on these graphs. But I wouldn't have known that there were a lot of points up here. And again, these are also somewhat arbitrary. You can do these and change those numbers however you want. The point is to plot it and learn what my data look like by using it. This is clearly symmetric data. This looks beautiful. I didn't make it that way, so obviously it's a class example, right? This is definitely not good symmetric data. And so then the analysis techniques I would use for this data are going to be very different than the analysis techniques I might use for these data. And I've been able to get that just from the graph. So I think I answered your question. Did that help? You can specify what that value is in your software. It can be 1.5 times or just 1 times. So it really becomes what becomes your preference. What have you found in your analysis or whoever you're working with analysis to be the most useful. And it depends on what kind of data you're dealing with too. Because if you're dealing with something that has a very small range, so like A1C, right? You're dealing with A1C. A1C values typically go from something like 4 to, if you're somebody super diabetic, and I've had people in data sets 20, right? So that's really kind of the maximum range you would see. So 1.5 times interquartile range might not be exactly what you would want, as opposed to something that's much broader, like say systolic blood pressure, which can go from 85 to over 200. So one of the things you learn in my class and listening to me is that there's never one answer. It's always it depends. And I'm sure if you've ever worked with David Redden, he's probably said that phrase a lot. It depends. So I've talked about 2 different softwares here, and I haven't really done a good job of talking about software. So typically, us in biostatistics here at UAB, we will use one of 2 software. SAS, which is a product out of Cary, North Carolina, that costs a lot of money. That is the typical statistical software used by the government. So if you're doing any drug trials and those things, they really require you to use SAS. And it's kind of still the standard for statisticians most places. The other is called R. R is a free statistical package. How many of you have ever heard of R before? Oh, good, great. R is starting to get more of the market share, so to speak, even though it's a free downloadable program, simply because smaller institutions, smaller companies, smaller groups can afford free. Sometimes you can't afford the $25,000 it costs for a yearly basis of a SAS license for one license. You can't afford that unless you're a big institution like maybe. So R is starting to show up more, and places like the FDA are actually working on making sure that R is verified to the point where they can accept R analysis when you're doing drug trials. And once that happens, SAS is going to be in real trouble because nobody will want to pay for it if you don't need it, quote unquote. I love them both. I have them both open on my computer at any point in time. Are there other statistical softwares that you all use, Matt? Stata?
Yes.
Stata?
But I mean, I primarily use SAS.
Stata is an excellent package as well. And in fact, the story behind Stata, I don't know if I got it exactly right. The story behind Stata was that people wrote SAS, had some friends, and they got mad at each other, and so then they just went and made Stata because they were, it's kind of like, well, I'm going to go make my own team. Stata is a great package. It's used more, I think, in epidemiology departments than it is in biostat departments, but it's still excellent software, and it's half SAS and half R. Stata has a set of modules that are fixed and written by the company, and then there are a lot of user modules. So if you wanted to write a package in Stata that allows you to do some fancy analysis, you could write it, and Stata would approve it or not approve it, and then you could download it and use it. So it's half user written and half built.
All of them are Python-based, right? So if you're familiar with, the language in one program, it's probably not that hard for you to pick up the language in the other programs, or is R different?
R is difficult, in my opinion.
So some of them work that way, yes. So the question was, for those who might be on here, it was, if you learn one or you know a programming language, can you use it for another? And the answer is, it depends. So SAS is a procedural programming language, meaning everything is either a data step or a procedure step. Meaning, if I want to run regression, I have to run proc reg, and everything in there is unique to proc reg. So the programming techniques there are unique to it. If I run a data step, the programming there is kind of unique to the data step. Whereas R is much more similar to this thing called MATLAB or C+, if you use those. R is a much more true, quote-unquote, programming language. SAS has a programming language, and I'm putting air quotes here for those who can't see me. It's called IML. That allows you to do things that are R-like, but IML predates R by quite a long time. And a lot of students who have not got a real strong programming background, meaning they haven't done a lot of computer programming in undergraduate, tend to gravitate toward whatever they learn first, and it tends to be SAS, because SAS has much less programming requirements. And they also tend to gravitate toward statistical software that doesn't require programming at all, like JUMP or SPSS. And GraphPad and Minitab, and there are a lot of them. I tend to want to do the programming ones because I want to have control over it. JUMP, if I had to use a GUI, a point and click one, I would suggest JUMP, because JUMP is a SAS product, and it's better than SPSS. Don't quote me on that. It's a personal opinion more than an empirical decision. But typically we teach R and SAS. Emily?
Can I make an editorial comment? So I think that for all of these, one of the important things is documentation and making sure that your results are reproducible, right? So I think, as part of the CTS, we talk about reproducibility. So the programs that don't require you to have code usually will generate code for you. So if you can, please do that. So if you're using SAS, you kind of have to write the code, so it's easy to document it. R is similar. You can do it as a line. So but if you're doing SPSS or if you're doing Stata,
download and save that code so that you can get back to where you started. Right, so you can go from your raw data to your results. And I think that is, at least from my perspective, more important for which specific software you use. Different ones have different strengths. I would generally not recommend SPSS except for individual level modeling, and there it's much better than what SAS has. So just keep it on.
Did you say multi-level model or statistical equation model?
Multi-level or structural equation.
Okay.
Both of those, I think it's much more sort of social science focused, and SAS doesn't. They don't do it, but it's not elegant.
So for those of you who are listening in, Dr. Levitan made a great point in that it doesn't really matter which software you use. What's more important really is making sure it's reproducible, meaning you save your code or you save your script, which is what it's called in Java. And so that way when you open it up again in a few weeks or a couple months when the revise and resubmit comes back, you can actually figure out what you did so that you can change it. But yes, that's a great point. Thank you. So why do we look at the data in graphs? So why are we doing this? Because at the end of the day, I don't really just want pictures. I want to make decisions, right? I want to be able to answer hypotheses. Well, what we call answering these hypotheses are made up of two pieces: estimation and inference. Meaning, I'm going to estimate some kind of number, i.e. an effect or an association or a mean difference or something like that, and then I'm going to do inference on it. I'm going to make decisions based off of it. So the key assumption for most 1 and 2 sample tests that you kind of cover is the data are normally distributed. And that one is almost uniformly assessed visually, meaning you use something, I thought I had a QQ plot in here, I don't. You use something like this to say, oh, the symmetric data look really good, nice and symmetric, so I think normality is okay. I can call this a normally distributed random variable, as opposed to the non-symmetric one, which I can't. There are special graphs that I probably should have included here. One is called what's called a QQ plot. Has anybody ever heard of a QQ plot before? A QQ plot basically is a plot of these data that get rid of all the particulars. If the data fall on a straight line that goes through the slope of 1, then you can say the data really are normally distributed. And if it deviates from that, then you have to stress and try to say, is it close enough? It's like looking at abstract art, right? If I look at a QQ plot and say, I think it's normally distributed, somebody else can come up and say, I don't think it is normally distributed, and we're both right. It's abstract art. So it becomes a subjective measure. There are tests for normality. Some of you may have heard of the tests for normality, like Kolmogorov, Smirnov, or Shapiro-Wilks, or there's another one that I just can't remember its name. Those are used sometimes as actual tests. Are my data normally distributed or not? But those can be bad when you have large samples. So it's kind of the opposite of what we tell you. More data is better, but not if you want to use these tests. In general, estimation, those are the sample statistics we use to estimate these population quantities. Because the sample average is not the population average, but we think that it is. And what's the population? So if I take a sample of children born at UAB hospital, that's my sample. What would my population be? All babies born in the U.S., all babies born in the world, all babies born in Alabama, all babies born at UAB, all babies born at UAB on floor 2. What would the population be?
Depends on your question.
It depends on your question.
On what you're trying to answer, I guess, to what kind of inference you're trying to make.
So, use a Willy Wonka, strike that, reverse it, okay? The sample is dictated by the question and the population, right? So, if I wanted it to be something that's more representative, not just UAB hospital or Alabama, then I would need to sample it that way. So, if I just sampled UAB hospital, my population kind of gets forced to being something like all babies born at UAB hospital, not all babies born in the United States. That's why you have multi-center trials or multi-site trials, so you kind of get at a bigger population. But that would be the population, meaning the group you want to talk about. But I can't talk about all of them, so I have to pick a smaller, and that would be my sample. All babies born in the month of August, because that's when my money came in. Right? Inference, it's making the decisions about the population based off the sample observations. So I really want to talk about all the babies born at UAB hospital, but I only have this sample, but I can then make estimation and inference about that larger population. Are the average birth weight of babies born at UAB hospital greater than 2 kilograms or 2.5 kilograms, whatever underweight's considered? I can't. I want to test to see if all of our babies are born at not underweight. That would be making a decision. Basic inference for continuous data, the basic one, the most basic, is what's called a one sample test. Meaning I sample my one group of babies here at UAB hospital, and then I run a one sample test. Is their mean different from something? This is sometimes called a one sample z-test. And then it assumes the population standard deviation is known, meaning I don't use my sample variability, I use some greater variability. So maybe I go and talk to somebody who has all the data for all of UAB hospitals' births ever, or at least all the ones that are electronic, and I take that variability, and I call that the population variability, and I assume it's known. Most cases, that's not possible. You can never really have the population standard deviation. So we teach you in these courses, oh, here's a one sample z-test. Let's do all this stuff with the z-test. And then we say, yeah, you're never going to get to use it, so let's go on. So I don't want to waste your time on it because you'll never be able to do it in real life. Most of the times what you do is you have a sample, and you're going to need to use the sample for both the measure of the mean and the measure of the variability. And when you do that, you typically are going to use what's called a t-distribution or a t-test. And the t-distribution is a symmetric distribution that looks like a standard normal, meaning a normal random variable, as the sample size increases. And it is parameterized again by these degrees of freedom. And it's an n minus 1. We still lose 1 when we talk about a t-distribution. The story of the t-distribution is really fun if you've never heard it. There was a guy who worked at quality control for Guinness Brewery, and they were upset that they were breaking so many barrels of whiskey. Whiskey? It's not whiskey. Guinness. Beer, yeah. Whiskey. You can tell I don't drink. I don't know. Guinness. And they were upset they were breaking so many barrels. And they went to the quality person, Will Gossett, and said, we want you to figure out how to break less barrels, but we can figure out if our quality is still good. And he goes, well, statistically, I don't know what to do. And he figured out, and he invented the t-distribution to be able to destroy less barrels of Guinness. But he knew that if he showed the Guinness people this, that they would keep it and hide it, and he knew that it was important. He knew it was more important than him. So what he did was he published it in a journal at the time, but he published it anonymously as student, so that Guinness didn't know that he did it and wouldn't get any of the money or copyrights from it. So the student's t-test, the student's t-distribution was created. Most people are like, well, who's this guy named Student? Well, it wasn't. It was for the betterment of mankind that he did this. And we are very thankful, because most of modern statistics kind of derive from this t-distribution to some extent or the other. So, so we're good. And it works with very small samples. And then what you do is you would take your data and you would transform it. You would subtract away the mean or the sample's mean, and then you would divide by the sample standard deviation. So you would scale it down to where it was a variable that had mean 0 because I subtracted the mean, and variance of 1 because I divided by the standard deviation. It's called the t-transformation. And by the central limit theorem, which is the central theorem to what we do, X bar, the sample mean, is approximately normally distributed with mean, population mean, and variance, population variance divided by n, where n is, again, our sample size. So the central limit theorem is really cool in that it says that the sample mean eventually goes to a normal distribution, and its variance is scaled by my sample size. So if my sample gets larger, my variance is going smaller. So that means if I actually end up having 100,000 observations, it's a random variable with near zero variability, meaning I've got almost exactly a point estimate of the true population mean. So the central limit theorem is really cool. And by that, and that property and our t conversion, we see that this is our t statistic, which is the difference of x bar and the mean divided by this standard error, and then it's a t with a degrees of freedom n minus 1. So I would run my one sample t-test for the hypothesis that the population mean was equal to some number. I say here mu naught, some number, 10, 100, 40, whatever. And then I would calculate t star, the test statistic, and I would calculate a p-value. Conversely, you can calculate a critical region and see if your t statistic fell in that region. But most people want p-values. Everybody wants p-values. Is it less than 0.05? Calculate p-value. It's useful to see if your sample has the same sample as some population or other group. For example, the CDC states that U.S. men have an average BMI of 26.6. Does your sample of Alabama male patients have the same average BMI? So I can take the sample of the men here in this room, calculate our BMI, take the average, and run a t-test to see if it was equal to 26.6. Mine is not. What's much more common is a two-sample test. So you're going to compare two groups instead of just one group itself. You collect data on two groups of people, independent groups of people, I should be clear. This is the independent sample. So, for instance, you may have cases and controls, or males and females, or above age 40, below age 40 patients, something like that. And the interest is testing if the population means are different between those two groups. Here we would use a two-sample t-test. But the data need to be normally distributed by group. And this is where I see a lot of students and people make a mistake when they start doing a two-sample t-test, is they run a histogram of their data. They just run a histogram of their data. It looks normally distributed. Like, no, you have to run it by your groups. Meaning I need a histogram for males, I need a histogram for females, and they both need to be normally distributed. Meaning, if I run the box plots, they need to look very symmetric. If I run a QQ plot, it needs to be a straight line, those kind of things. If I run it overall, that just says, oh, overall the Y's could be it. And I have a toy example when I teach class of a Y that's perfectly normally distributed, but it turns out that this half are the males and this half are the females. So it's a horrible example to do a two-sample t-test, but it shows you why you'd want to do them by group. So then we want to look at our descriptives by group, which is why you see a lot of times in this table 1, like we were talking about before, you'll see mean and standard deviation or median and IQR for males, and then mean and standard deviation and so on for females. And then potentially a p-value that would compare the two of them at the basic level before you do your other more complicated stuff. The normal assumption can be difficult to assess in some cases, but the data still needs to be mostly symmetric. That's really the key, is try to look for symmetry. That's really where you want to use the graphs. It's just kind of look and see, does it feel good or feel bad? Because it turns out the t-test and two-sample t-test is really robust, meaning that if it's not quite normally distributed, it still does really well. But if it's not normally distributed at all, it's not symmetric, then you have non-parametrics, which we're not going to cover today. There are two types of t-test, two-sample t-test. There's one with equal variances and unequal variances. Can we assume that the two groups have the same population standard deviation? Meaning, is the variance among males the same as the variance among females? If I can't do that, then I need to assume an unequal variance t-test. And there are tests to say, are the variances different or not? SAS runs it automatically in proc t-test, and you can get it out easily in other software. Testing if the variances are equal. And here are some more formulas, which I know everybody really appreciates and enjoys. This is the formula for equal variance two-sample t-test, and then the unequal variance two-sample t-test is below. The thing I would want to point out is that the degrees of freedom for the equal variance is really straightforward. It's the size of each sample added up minus 2. So if I have 50 males and 50 females, my degrees of freedom are 98. If I'm using unequal variances two-sample t-test, the degrees of freedom are much, much more difficult to understand. It's a function of the variances of the two groups and the visions and everything. And the number that goes in here is sometimes called the Satterthwaite approximation. So unequal variances, you would not want to run those and try to do them by hand and then look it up in a t-test yourself without going and consulting a book to figure out the degrees of freedom estimation. Can we compare more than one group on a continuous variable, or more than two groups, I should say? Can we compare more than two groups? Yes, we can. It's called ANOVA, which is the most uninventive name of anything I think I've seen, at least in statistics, the most uninventive name. ANOVA stands for Analysis of Variance, A-N-O-V-A. Right? If you thought it was some kind of exotic thing, like it was named after something, no. Basically just took the abbreviation and made it sound like a word. It is basically a generalized equal variance two-sample t-test. So I take all the stuff we talked about with two-sample t-tests and I blow it up to multiple samples. So a potential question is, does the average A1C value diabetic patients differ by race? So I consider race as a categorical variable and I want to compare average A1C values for each of those. This is completely made up data. My races here are X, Y, Z, and W. But this is a box plot of potential A1C values by 4 different races. And you can see this box plot with multiple groups is a really cool picture. The ordering of the x-axis is arbitrary. You could rearrange it however you want. A lot of times you'll see people that will arrange it to where the smallest one is first, and then the next biggest one, and so on and so forth. So they're going up or they're going down, but it's really quite arbitrary. Unless you have some kind of order to your groups, and then it makes more sense. If you're looking at BMI category at the bottom, then you might want to consider just leaving it that way, but otherwise you can change it around. But this kind of tells me that this group seems to have the highest median. This group seems to have the lowest median, but all 4 of the groups seem to have about the same variability to some extent, because the boxes are all about the same width, and they all seem to be fairly symmetrically distributed because the bold line is almost in the middle of each of those boxes. So this plot has been able to tell me a lot of information immediately, that Group W has the lowest value of A1C, Group Z has the highest value, but equal variance assumption might be okay. I might be able to assume that these groups are equal variability, all from this one picture. What ANOVA does is it compares what's within the group variance to what's between the group variance. And I'll come back to that notion in a moment. Between group variance is this horrible formula, which basically says I look at the distance between each observation and the grand mean, meaning the overall mean of y, and then I get its kind of variance. I take those differences and square them, and I sum it up for every person. Or, that's the between group. So the within group says, oh no, this is not each person. Let me start that again. My apologies. I'm trying to go quick because we're running out of time. Y bar j is the mean for the jth race. And this is saying the mean of the jth race is some difference from the grand mean of all the y's. And then you add this up for all of the groups. So in this case, this would sum from 0 to 4, or 1 to 4, because there are 4 races. Here is the difference between each individual person and their group's mean. And I sum it up. And then I compare if this guy is bigger than that guy. And if the between group variance is bigger than the within group variance, then I would be able to say that my means are different. And then here's the F statistic, which is the ratio of this thing, SSM to SSD. That's all well and good, bunch of numbers. Let me show you some pictures. These black dots represent a group. And in this example, I'm only going to use 3 groups just to make it easier on ourselves. So I don't want to use a bunch of colors. But these are the outcome values for group 1. And so there's no real y-axis here. It's only the x-axis. So these are those dots. Here are the dots for group 2, the red dots. So clearly, the red group has a different mean than the black group. But they still seem to be spread out about the same if I go between the black groups, black dots and the red dots. And then here are the green dots, the third group. And they go on their place. And they seem to be kind of in the middle of the red and a little bit of the black. So these dots represent the group means. So this dot here is the mean of the black dots. The red dots, the mean of the red dots, and the green dots, the mean of those dots. And so the SSE variable, the within group variability, says I take the difference between this mean here, this black line, black dot, and each of these individual black dots. And then I sum it up. And I do that for all three groups. So I take the individual observations from their group means. That becomes my, sum it up, square it, sum it up. That becomes my within group variance. I take these mean dots here, and I take their difference from the overall data's mean, which is here, this blue dot. And I take the difference between this dot, square it, that dot, square it, that dot, square it, and I sum it up. And that becomes my between group variability. So these dots are within the groups compared to their own mean, and this is the between group means to the grand mean. And if these dots here are more spread out than these dots here to some extent, then I would reject my null hypothesis. Therefore, one of my group means is different. Does any of the groups look different here? What does it look like? Who said that? Is that you, Matt? Okay, I couldn't. This thing's running, and so I can't hear. Hearing's bad. Yeah. And it turns out, without showing you all the numbers, that that's exactly the case, because these are all about the same, equally spread out within the groups down here. But the group means themselves are very spread out, so that this would give me evidence that the group means are different, and in particular, the black dot is different than the green or red dots. Here's another example in which there are no difference. Here there's the black dots, here are the red dots, here are the green dots, here are these dots. Now, the mean dots look to be about the same spread apart as the previous plot, but look at the individual data. The individual data are all kind of within each other, and the black dots are actually more spread out than the red or the green dots. So I've got a lot of variability kind of down here within my groups, but not as much variability between the groups. So that if I ran this in ANOVA, this would not reject. So this is why the F statistic, which people talk about as the global F in ANOVA, why it rejects for large values of this ratio between and within group variability, is because it literally looks at does within this group, on average, differ from between these groups and the grand mean on average. Questions? You probably were wondering why I had so many slides. Now you know I had eight pictures that were just dots showing up on the screen. But this is why ANOVA works. This is why the F statistic works, and why we talk about between group and within a group. Because this is literally a visual representation of what happens numerically on this stuff here, which most people, we look at this and you're like, I can kind of get my mind around it. But hopefully this representation here, where you see where the differences are and what we're measuring, is a little bit helpful. So once you reject ANOVA, I reject there's at least one group different. It doesn't tell me which of these groups are different. So then after I do that, I have to run what's called post hoc comparisons. Has anybody ever heard of post hoc comparisons? There are several common types of post hoc comparisons. Tukey's, Bonferroni, Scheffé, Dunnett's test, Dunn's test, Fisher's significant difference or whatever. Some of them you should run and are very good, like Tukey's or Bonferroni's or Dunnett's, if you've got one control and you want everybody versus that control. But some of them are less good. I'm not going to say them out loud because I don't want to get in a big conversation. But when you pick your post hoc test, pick it before you get your data. Pick it beforehand. do it what we call a priori, because the choice of this post hoc test is very important. And the post hoc test is only run after you have rejected the overall F statistic. If there's no difference between the groups at all, why would I want to look at individual groups versus each other? If this doesn't reject, I don't do this. I've seen so many people skip straight to the post hoc test and go, ooh, look, this group is different from that group, when sitting at the top is an insignificant overall test. So it's an order. Run the overall test, and then you do your post hoc test. Are my groups different? Which groups are different from each other? And pick which test you're going to do a priori. Think about it ahead of time. It's one of the reasons why you want to come to somebody in Bird, or myself, or Dr. Levitan, or somebody like that when you're planning these things, because you want to think through what is the right way to do this analysis. If you have more than one variable that defines your groups, that's sometimes called a two-way or three-way ANOVA, meaning if I looked at, maybe I was looking at men and women, and then I was looking at race. And I thought, well, maybe there's something about what my outcome is that differs by race and it differs by sex. So that would be a two-way ANOVA, because I have two different groups, two different variables defining my group. And the math kind of works the same way. It's just a much more complicated picture. You can also control for continuous variables. If I want to control for age or something else within the model, I can use what's called ANCOVA, which again is very uniquely named. ANCOVA, analysis of covariance. But I would argue that in any of these, you're actually really doing a regression. ANOVA or ANCOVA, all this is our linear regressions. And so the next step for me would be thinking about it in terms of a regression. And that is where we end, because as I told you at the beginning, this was followed by a regression talk by somebody else. So are there any questions? We've talked about how to summarize continuous data. We've talked about how to do some simple analysis, one group, two group data, and then we've talked about ANOVA, and hopefully I've given you a better idea of why the F statistic in ANOVA rejects for large values of within versus between variance. Any questions? Great. Well, thank you all, and it's been a pleasure.
We do. I do. So I have, this was good. I was going to make it. Yeah, I like that. Thank you. I was 11 and I got back here and realized it's at 10. Yeah, I was when it comes to this short. Yeah. A lot about stuff figuring out. Unless it's a no-show, oh, okay. See you later. So I like your graph for the notes. That was so nice.
We're just gonna talk about like what would be possible, like.
Yeah, but you want me there at 12:30 or what?
No, we're not.
Okay,
I'll see you soon.
because Liz and I are looking at it an hour and 30. I always want to let's do it. I wonder if, well, we probably can find out how we're teaching our student, our PhD student, like how to review or
How do you like to
sharing a coordinates versus like writing. You know, you can't. Yeah, I assumed that Harvard was going to
To me, it's, I would call it.
Yeah, it's pretty easy to look at.
Yeah.
Somebody-
Is it still softball season?
I
or not?
Yeah.
But
small.
I
Like right
had
after
more programming before I came to statistics.
Yeah, see, our students have not had any,
Right.
but they are learning
Saturday,
hard,
we're
so that's
in
good.
the ballpark in eighth.
Yeah,
Because it was a-
yeah, the
it's
teachers
a-
Fact,
Well, you have students who are
So it's
wanting
fun.
more,
It's still
and
not
they're really
involved.
interested in art.
Oh, yeah. No, I mean, I was a catcher.
Okay.
I was a catcher when I played softball, and our season started, you know, in mid-August.
So you have some students who are like, oh,
Yeah.
this is really,
It's
I really
borderline
want to
child endangerment.
Okay, yeah.
See, our statistician does a data management class, but he teaches them SAS and R in the same class.
Yeah, they all
So, yeah, they do that class, it's required.
We had that.
I'm like, it's
we
an
were
important
both,
job,
and
I'm
we
like,
realized that, at least for our students.
the action of being catcher is rare,
Either one.
you know.
Well,
So now they have semester.
the action and
And
catching.
the full semester bar.
Wow, well, I'll let ours know in case there's some that have difficulty and need more. Thank you. Yeah.
If you have to take the classes at Chick-fil-A,
Uh,
you're gonna get the basics. Just
Yeah.
Since kind of got me.
Necessarily.
That's,
uh-huh.
Byron Yeager, he, I've been using R for a long time. He showed me some code from his dissertation.
Yesterday or today?
The right person. The right person is
Really
cool.
cool.
Oh.
So, yeah, you have some students that are really interested. They've already got what they need to
Then,
go to the straight,
10
but
minutes until
have a back and
way up there.
Right, yeah.
Might as well.
Trying to sit on it, have you tried to sit in on a class?
No, yeah, we're taking that over for it.
I tried this semester to sit in Dr. Rogers' data mining class.
I'm assuming.
I missed one class and like, I can't get back to it. It's just, you don't have time. You don't have time for professional development.
Out of town today, but
Yeah.
I'm sure they'll let us know anything about it.
That's where I am.
It is hard. I wouldn't mind taking the art class,
So I have that,
but I
you know, desk
commit to that.
7 years. And then I have a chair. that
Have a good day, thank you so much.
Yeah.
And then I would, to myself, so like, if these are new chairs,
Right.
new desks,
Already an upgrade, yeah.
yeah, it's gonna be great.
Well, as I told the others, I had a scheduling mixed up with time difference. I had an interview at 10, but I thought it was 11, so I wouldn't be able to come to this meeting. I was on the East Coast at the beginning of the week, so I didn't think about that, but, I will, of course, be at whatever the next one is. I just will not be able to be there today. I have to do a qualitative interview. It's about 30 minutes, so.
Good luck with that.
Thank you.
So we're gonna do this every 2 weeks,
That's what it sounds
or
like.
we probably meet every week, but the writing group is
Right.
every 2 weeks.
Yeah. I think will be useful. I was looking forward to writing today, but I guess I'll have to do it later.
Well, I'm assuming today we're just gonna talk about it.
Oh, that makes sense. That makes a lot of sense. Get an established idea of what we want out of it. I guess.
Yeah. I need to get a lot out of it.
Yeah, same here. Same here. Well, I look forward to hearing however it goes and what you
Yeah, we'll
guys
send you
decide.
a kind of a summary of what we talked about.
Okay.
I'll try to take good notes. I'll volunteer to give a summary.
And I'm very open to, giving each other feedback or just spending the time writing. I can use either or.
Yeah. Anything related to writing.
Right, exactly.
Bye.
You know, where you're looking at that last one, it was like, wake up at 5 in the morning every day, like, wow, like, hey, chill. Wow. Hey. Yeah, I just didn't want classes. Like, I started off the semester with trying to be 5. Oh, there you go.
I'm not taking classes. Yeah. Because, I would love to.
Yeah.
I told them, I said I would give just one class. Because I'd like to take biostats.
Yeah.
I think statistics.
There's like a lot. I put Laura actually in one of the classes that we did. This is useful and also this is like 2 parts. Really good.
I might regret not taking classes later that
but I just haven't taken any classes so far. I'm teaching and, so it's a new grad class and it just takes a lot of time to do that. And, I don't know. But like, I'm the carpool guy in the morning and in the afternoon, and it was just like, so my schedule is limited at the middle of the day, and then in the afternoon, I pick her up, and then I'm observed. Sometimes she goes, yeah, when am I gonna work?
How old?
So, she's 7.
Okay.
And I took her softball team too, so we had practice Wednesday, Thursday, or all day Saturdays. I'm taking a class right now.
Oh,
I don't know how to do it.
God, it's so crazy how like, it's been traditionally say like multiply your credit hours by like 4 or something. I was like, oh, no way, I'm not gonna spend that much time. And it's like quickly realizing that it does require like, so I don't.
Easy was doing it, see, I'm not so expensive.
Yeah, exactly. It means, I don't know. Because like the entire A is just like hating myself right now. Because like last week I just didn't do an assignment because I was like, no, I'm just, I don't care, I'm gonna just take a hit. But it was just like,
It's still hard, yes.
No, I'll let that roll on here. You can play. So what do you guys want to do today? Like I'm ready. I have to make a mental work on everything. Okay. I hate you. She said that she kind of needed yeah, just reading this feedback. Then know if there's any one should work on, or maybe we just set like what. And I'll be okay. And with email.
Well, Whitney said before she left, she said that she is okay with having the times right during this group, or reviewing each other's writing, or
It's all.
Yeah, it's not like, yeah, I got it. Like, very last one, something we're all gonna have to take a look at. Like, this will be it for me. I'm done, everything else is getting rid of, that's an enneagram,
Yeah.
so, yeah.
I like that, we'll split it up each time.
How great it is for.
Well, the group is supposed to 11.
Okay.
I think that's what, one sent email and said, like 9:30 to 11. So. Well, you wanna share with us and then we can.
Oh, sure.
We should
figure on the other side of stuff, but yeah. So this is like a baby grant, it's not a huge thing. I mean, it's
What kind of grants is it?
so I'm looking at. So it's basically looking at making it come in with early stage breast a little bit lacking in terms of breast cancer. So it took me a while to refresh that, but, yeah, this is such a cool project. I think some of the things that I was wondering about is, I've never written something like this before, so I don't know, how much you're supposed to include here versus when you go on to the more in-depth. I just don't know, but, some of the things I was wondering here is like, okay, well, are you talking about side effects, or are you talking about survival, things like that, but you did address it here.
Yeah.
So is that, like, for,
Yeah, that's more of the same line, so, yeah.
So how long is this supposed to be?
4 pages,
Okay.
it's a short page.
So you used all the space that you could.
Yeah, well, I mean, part of the comments that I got, figures are too small, people can't read them, so I did that text just to make the figures small, So.
I did wonder about what is this working,
So I can't, like, that is gonna come from a patient's own. So that's the thing,
like even things like side effects?
yeah, because the qualitative, the interviews are fine, I mean, so people who have chosen to go to radiation, that's a lot of people like and all that stuff is based on condition, not which. So basically, we're using their PR to guide us on all these conditions. In the same way that I'm using my API instead of okay. So that's what it should be optimized. This is what I said to try.
So we're going to inform 5, but
Yeah, so if that doesn't come across,
Are you expecting, what is expected, their perspectives?
Yeah.
Side effects, whether they match what
yeah.
the data show already? Okay.
The data says it's frustrating.
yeah, maybe clarify like reported by patient or something like that.
Okay. Report by patient is part of the
Because that's the important part of
Yes,
this, is
right.
getting the patient's perspective.
Yeah. Okay, fair enough, I'll do that. With the breast cancer guidelines, like, part of what's hard about these things, you have to like cram as much information as possible, and like, the short says is that, so did that not come across, like, when you have to refresh yourself on guidelines, because this is specific to me, you would never know these guidelines. Right. You wouldn't, unless you're a primary care physician, and your patient comes to you and asks, you wouldn't know.
No, I think once I got through the background, I could, tell that it was either, radiation or hormonal therapy or both.
Okay.
So, that came across pretty clear, I think.
Okay.
The 3 sort of options.
Okay.
I did think that, here, like, I thought this was an important point, and maybe, compassion, like the one where you talk about your study, and, like, with older women who have a mission also,
Okay, fair enough, yeah.
I agree. We don't have anything bolded on this page, so it wouldn't be overdoing it. But
Okay.
that as well, more italics.
People more often you do this, or I don't understand examples for people.
Another writing group, and it depends on where you're submitting this to and
Yeah.
what they're expecting from you.
Yeah.
Some of them say don't overuse bolding or italics or whatever, but if you don't have any bolding on the page already, that's a key point that you really want to emphasize. I would bold it. What I keep hearing about these is that people are not your reviewers are not going to read this word for word. They're going to pick out certain things that they bold it. That's where their eyes are going to go.
Okay, good point.
That's where you're going to drive it home. Especially for people who have a background, they know all of this.
Yeah.
They're just going to sleep over it.
Here's your graph. Fill in the file, minor edits. I mean, that's an important point to. If you want to send your life expectancy, there's no difference. What gives you the least for treatment? Because if you don't, you do have their risk of recurrence. Now, that recurrence can be salvaged. Yeah. Again, it's another, it's another procedure that you have to go through more surveillance, and you have to, for some people, like it's black hole content. Like, listen, there's no like on that.
Oh, so you do comment on that here?
Yeah, but I don't put it in today. That's a good point, I'll put it in there. I'll put a line saying, yeah, I'll put a line.
Yeah, because you say that it's a little bit results, so.
Okay.
I'm not a topical expert.
That's okay, that helps.
I didn't have a lot of concerns about that. But
Yeah.
I can understand from reading it,
Yeah.
like I said, from your.
No, but that's
seem to
not-
include everything where you need to. There's just a few little things like, here you underline 41 to 72%, 2 71%, here you dash. Or
Oh, okay.
You can do this finish.
Gotcha.
Or do Social Security Administration capitalize.
Okay, fair enough.
Well, I mean, you stare at it so long too.
Oh,
So, on specific aim one,
Yeah.
so identify decisional needs and ultimate making decisions.
Yeah.
Okay, so decisional needs, making decisions.
Gotcha, yeah.
Redundant, so anywhere you can reduce words, like
Yeah.
identify decisional needs and ultimate related, or even, about.
Okay, fair enough. That's great, yeah.
Because then you can add more words here.
Yeah.
Here where you say small volume treatment center, we're more likely to centers.
Okay.
Continue the underlying through recommendations.
Okay.
Elicit the E.
Okay.
That's elicit. Illegal information.
I know, you're good. You're good for this.
So, additionally, they were not interested in, I think it's probably or even, or you can even drop the E if you say specific details. Results of this analysis would be used to help. You can say the results of this analysis will help design our interview guide. And I know you talked about these are great.
Yeah.
But this information about what you're going to include in the questionnaire will also be another mini table instead of text.
Okay.
Just bulleted information. I'm not sure how you would design that, but like that would be.
Okay.
Because you put this in smaller fonts, and then it would be just a smaller.
Well, we're allowed to small ones, this be 11.
Well, whatever.
That, the image they, I think, that's more.
Okay. But this is.
I have to say 11,
Okay.
unfortunately.
Wow, you would.
But no, it's even makes more sense because we'll look at that. See, this is helpful, because those are comments I'm going to do about content. It's not as much about structure. Yeah, sorry. You know,
I'm telling you, I'm in that other writing group.
oh, yeah, me, yeah. We can do it now, I know.
Well, I recommend it. It's called the National Research Mentoring Network.
Oh.
Have you heard of that?
Yeah, I thought about it, or I didn't get it until so late, but.
Okay. thing, but then you're assigned to coaching groups with a
Yeah.
coach who's familiar with how this works.
Wow.
And with different kinds of grants that people
Yeah.
apply for. So a lot of people were applying for aids, and mine was applied for an NIH loan repayment program. You know, just various things that people apply for. The person that was my coach is a grants person at the university.
Oh my goodness.
So they pick the people to be coaches who know exactly what they're doing and have done all these different grants. And you have a cohort of people who are also doing this. So you meet every 2 or 3 weeks for 3 hours, 3 hours, but 3 hours on face to face on the computer. And you get 45 minutes to go over the person's word for word.
Oh my goodness.
So yeah.
Wow,
Yeah,
that's great. So how do you apply for this? You just I didn't apply for this stuff, because it didn't work my schedule. I applied for like one thing, like literally the day before. I think that they said it should go to school like 9 o'clock.
Yeah, because there is a demand for it. But, like this would be a perfect thing to submit. Like if this were your application, this would be perfect for sending them your specific candidates.
Absolutely.
And then if you work on tweaking it, and mine completely changed from the time I started.
Really?
To the time I ended. And now it's better. So I mean, I don't know if I'll get granted, but their goal is to try to get everybody's grants accepted for applications. So yeah. Yeah, it's a bit of a but yeah, that's one of the things that they would say when you have just a lot of text that is just saying what you're going to do, then it's easy to just put it in.
Got it.
Because people, and also people's eyes are drawn to those.
Yes.
If they don't read a thing, they'll know what you're said interviews will try to assess, but
So get rid of that, like, okay.
yeah. And you're not trying to, you're not doing it.
I'm gonna do it.
Tries a lot.
Yeah.
Right. So the women without, this is just a question, so women without diagnosis of breast cancer are utilized as their considered group. I think just need to simplify. So like the women without diagnosis, the group of women without diagnosis of breast cancer is considered more likely, just are utilized and they're considered a group more likely to be compliant. It's like the laws.
Okay.
Well,
It's a part of
if that's why I said it's just a question. Because I know those are always hard to.
Yeah, mammograms are compliance, so if you get cancer, you're gonna be more compliant. That's what I'm looking at, but that doesn't come across as very. Have a whole weekend, right?
Well, you could just say what women without diagnosis of breast cancer are typically more compliant with treatment if they're diagnosed, and then drop some of that other stuff. So kind of a more declarative sentence.
Sure.
Because you're saying you're using this group of women because of this.
Yes. That's awesome.
Yeah, it is. And that's all I have to say.
Yeah, that's very. Okay, I really appreciate it.
I'm good with the nitpicky things.
I would love it, Vicky. I love this game. Yeah. But it takes a while, just my informational errors.
I've seen it.
I feel like I have so many friends.
Especially in like genomics, that's where they're talking about different genes and pathways. So I think it.
This last sentence, that long-term health shown slightly higher but low overall risk.
Tell us the patient gets like that 3 versus 10%, so it's a little bit higher than 3%, but it's still overall with taking the trip.
Mike, can you just say it's low overall risk?
Yeah, I can say that.
I could see how, like a reviewer would say, they would understand that.
I think that's very round. Like that is so specific, so that's the thing that, like, we, it's, you just can't say it's about stuff. Again, but that's not, I don't think that's who's gonna rate this, I mean, that's very low round, so you're right, again, that's. Yeah, so it's a little hard. Yeah.
But, yeah.
Well, thank you so much.
Yeah.
Can I grab these from you now? So is it helpful for us to like do this kind of thing like at the beginning, like our,
That's great. And I mean, it helps us to review other people's too, because just think through how you.
Were you submitting this?
Well, I was, so I had.
You are, never what, you
Well,
are.
I'm doing it completely differently. So, so I have a primary mentor, retired. And she has been wonderful as a mentor while I was at graduate school. And she decided she was going to keep me as her last project. And what she wanted to do with what I needed. So, there was no way that she just supported last year. And I know people were listening paid to you know, so early in there, a lot of but now, then I go back to her and say, you didn't do this, right? So, now that it's so hard. So, the year passes, I continue up to do any right, doesn't take it's changed.
Yeah.
Papers here. She's still on.